Now we're on to question 6. We're on to question 6. Now question 6 is looking quite nice. So it says that the diagram below, not drawn to scale, shows an open cylindrical container made of metal with a circular base and a uniform thickness throughout. The length of the container from top to outer bottom is 120, and the inner and outer radii are 14 and 15 centimeters respectively. Now it says, draw a cross-sectional view of the container showing the measurements of the inner and the outer radii. Cross-sectional just means draw this face, all right, right here. All right, so all we're gonna do is draw the cross-section. Drawing the cross-section, we have a circle. Then we have another circle. We put this one inside of it. And that's what we have. All right, and then one of them has a radii. One of them has a radii of 15 centimeters, that's the bigger one. And then the smaller one has a radii of about 14 centimeters. And that's it. So the smaller one, the inner one, has a radii of 14 centimeters, and the bigger one have a radii of 15 centimeters. So what that means is that this right here, the distance from here to here is 1 centimeter. All right. So the distance from here to here is 1 centimeter. Okay. Nice. So we can proceed. So this is what we know. That's a cross-sectional view, of course. Now proceeding, it says, show that the capacity of the container is 73,304 cm3. The capacity of the container. Now the container is, the container is the one that is inside. All right, here's the container. All right, this is the container. All right, so we have the container which is inside, and we want to show that the capacity, want to talk about capacity is internal volume. How much can this thing hold? All right, so clearly it's the volume of the inner one. All right, the one with the radii of 14 centimeters. All right, so this is the diagram that we actually want. We want to find the volume of this one right here. All right, this is what we want to find. So we need the radii, we know is right here is 14, the volume. The radius is 14. And then we need the height. Now the height of the whole thing, including the metal and everything, is 120. All right. But the inner height now is going to be, let me see, the inner height. We need to find the inner height. The inner height, now the cross section from here to here is 1 centimeters. So what that means is the inner height is 119 centimeters. All right. So what we're saying then is that the volume, right here, the volume. So we're saying that the volume is equal to area of the cross section times perpendicular height. And the area of the cross section is pi r squared, because it's a circle. Pi r is 14 square times the height, and the height is 119, not 120, 119, because we have to subtract back the 1 centimeter for the thickness. So we're getting pi times 14 square times 119, and that gives us our answer. This is of course equal to 7,3304 cm cubed. That gives us our answer. Easy, soft, nice and easy. Now the next part of the question, it asks us now to determine the volume of the material used to make the container. Now the volume that is used to make the container is the outer volume, the volume of the big thing, minus the capacity of how much the capacity of the container. So I'm going to call this VC, the volume, meaning the volume of the capacity of the container. And this is how we're going to find the volume of the material used to make the container. So that is equal to the volume of the whole thing, which you know is pi r squared times h. It is pi r squared. Now r in this case is 15. So pi times 15 squared times h. In this case, the height of the whole thing, which we saw, was 120. And then, of course, we're going to subtract the volume of the inner volume, which is the volume that tells us the capacity of the container, which is 73,304. So you put this in your calculator. Remember, we're using pi as 22/7. So you put pi as 22/7 in your calculator. 22/7 times 15 squared times 120 minus 73304, and I'm getting 11,553 cm cubed. 11,553 centimeters cubed. And that gives you the volume of the material that is used to make the container. If you want, you could write this in liter. 1,000 cm cubed is equal to 1 liter. So 11553 divided by 1,000, that's actually 11.5 liters. Just to make your answer look more present, 11.5 liters. Or you can say 11.6 liters. Nice and easy, soft. Finally, it says, given that the density of the material to make the container is 2.2 grams per cm cube, determine the mass in kilogram of the empty container. So this is the volume of the empty container, 11,553 cm cube. 11,553 cm cube. All right, so you have the volume. All right. And it says, given that the density is 2.2 grams per cm cube, so they give you the density. Now they're asking you for the mass of the empty container. So density, as you can see, density is equal to, the sign for density is P from physics. So density is mass over volume. And so to make mass the subject, we're going to see that mass is equal to density times volume. And so the mass is equal to the density of 2.2 multiplied by the volume of 11553 cm cube. When we work that out, we're going to see that the mass is going to be 11,553 times 2.2. So the mass is 25,416.8. well, 0.6 grams. Now, of course, that looks like a lot of grams, so it's best to convert it to kilogram. Divide it by 1,000. We're going to write it as 25.4 kilogram. 25.4 kilogram. Now, this is a heavy container. This is quite a heavy container. Determine the mass in kilogram. Now, what kind of container weighs 25.4 kilogram? I have no idea. That's a heavy container. All right, because the containers that we generally eat our dinners out of is like 4 or 5 grams, sometimes lighter. And this is 25.4 kilogram. That's very heavy.